So it is Monday after all. Professor Eager, I believe, went all the way through his last lecture. Is that what he said on Friday? Or don't remember, wasn't there? I think it was his 12th hour. I don't think that he's got anything more left. So you guys have a week to put together that one-page summary, and it's on Stellar to submit. So that's the reminder here for his module. There will be a few people that just took some online module, then in which case they just do one of those for the first submittal. We're trying to make that a little bit more of a step-by-step process. Last semester we had everybody drop all their summaries at the end of the semester, and that's not really the way to do it. So he was done in September, so we should applaud. I will be spending the week with you guys, and if you remember, we're going to talk about a little bit of physical metallurgy, but we also talk about plastics at the same time. So last time we went through metal deformation and hot forming, essentially, rolling and all that. And today we'll do a little bit the same with the plastic after we've done through more ways that you form metals. I brought a bunch of little examples, and I hope that at the end of today we'll be kind of finished with how you get the shape of material when you do material processing, and then we'll move into a lot of other topics, like how you actually make it better in terms of properties and characteristics. So there are a few things that I've done in the past that work very well. This one, I'll spend at least one lecture talking about corrosion, because it's a little bit the complementarity to strength. It's easy to talk about strength when we talk about material processing, but a lot of times you don't select materials just based on strength. There's aesthetic that comes into account. There's a lot of parameters. There's cost, of course, but we think of corrosion as something that it really is controlled, because you know the metals, they want to oxidize. It's their natural state. It's the lowest energy. So when you have aluminum, it's oxidizing on the surface, but it's not a problem unless it's pitting and all that. And I find in the past that just having that discussion will help you have a better grab on why we do things certain ways. Again, just forming, we're going to go over both for metals and plastics. And if you remember from last time, it was all the hot steel and the fact that you have a cast structure that you're trying to get rid of. You start with something very big, you make it much smaller, it allows you to refine the grain. There's a lot going on when you do the hot forming, because at high temperature you have diffusion, you recrystallize grains. There's just a whole lot that happens that is good in terms of making the material strong and resistant. That's why when we think of forging, the idea to put the metal in the fire and then beat it up to make it better is a little bit what we do industrially, except that we do it on a continuous forming basis. So rolling is one of the mostly used operation to start from the big slabs and take it down. So I've already mentioned that if you go to a rolling mill, it's very, very hot in there. They don't need, heating system in the winter. It's just the process itself that heats the shop. And one of the reasons it does that is you're going through this plastic deformation. So when you deform, you create more heat. Just a little bit like if you have a radiator heating system with electricity, the electrical current through the system heats up the elements. So here it's by deforming that you create more heat. Do we use that in practice? Yes, we do. It's one of the reasons why they control the rate of deformation, so they're able to sustain the temperature that they want on the product. So after the big components, they leave the oven, they don't get heated anymore. They're essentially in ambient air, and it's the rate of deformation that keeps them hot enough through the entire process. So it's interesting for that. It's not what happens in cold working. But so this graph is a little bit on the detail about how you study engaging with the roller and how much you can reduce each time. This reference here is if you ever wanted to know a lot more about metal forming, Deator is a very good reference. What I'll say is if you try to, at each pass, to not reduce enough, what happens is your deformation is only on the surfaces. So if we start with the slab here and we just reduce it a small amount, it's really not a good idea. So we have a roller here, and then we have another roller there. So what happens if it's not enough, your deformation layer is only in this area, and you haven't done any work in what's in the middle. And that will happen sometimes and lead to essentially properties that are very, very different on the surface than at the mid-wall. So there is a minimum amount of reduction you want, so your deformation, your plasticity and stresses get all the way to the center and everything gets deformed. So it's not super common, but it will happen on products. So a similar effect of rolling here, because rolling, you can do it hot. You can also do it at ambient temperature. When you do it hot, your advantage is you're not limited by strain because you have this recrystallization, recovery of the steel, so it doesn't feel like it's getting deformed. It's healing itself at the same time as you're deforming it. When you follow the process here, when they say the temperature is 0.6 times the melting point in Kelvin, what that means is we're in a behavior that the steel will creep. It's hot enough that if you hold a piece of metal at that temperature, it's going to slowly get longer and longer and longer, just like a piece of plastic. So intuitively, that's probably why we can all agree that the material is just constantly reforming itself. Under a constant load, it's not acting like a spring, it's just deforming. And it's the same process that's helping it to heal or stay soft enough during this hot forming. You're talking about very high strain rate in some cases, and that's why you're able to generate enough heat. So 500% per second, you essentially take it this, and then all of a sudden it's 5 times longer in just the course of 1 second. So it's a very, very high deformation rate. Now, why would we do it at a colder temperature? Well, if you do it at ambient temperature, you can take a pile there of sheets or anything and put it in your roller, and you don't have to heat it up. So you do save on cost at the beginning. And also, because when you're done forming, the steel doesn't have to cool off, you don't have as much distortion. So the advantage of cold working steel is you get a higher strength because you just have this hardening without having the counter softening that you get at the higher temperature. Now, when we do that, let's say we have aluminum conductors for power lines. They have to be fairly pure, so they conduct electricity well. So what that means is unless you deform them, they're going to be very, very soft. So the way they do this is they will cold work the aluminum, big or small wires, to say 100%. So you yield, if we talk about almost pure aluminum will give you a yield strength that can be very, very low. So we talk about, say, 3 KSI, or that would be just 20 megapascal, yeah, something like that. Or less than that, not sure. I think that's the number, yeah, for yield. Is that enough? No, because there's a lot of tension in the power line. So you try to double or triple that amount, but what it means on the stress strain curve, because you're doing at ambient temperature, so if your aluminum typically will look like this, and then it starts hardening like that up to a strength, what you do with this cold forming of aluminum is you end up getting it to this point, so now it doesn't have as much ductility before it will break. So whatever you gain by this cold forming, you do lose it in resistance to fracture when you're forming it. So they take these in coils, like very large diameter coils for installation, and they have to be careful because they don't have something anymore that they can deform to 200-300%. And the only reason, again, here for this case of aluminum is you want to keep it pure, almost pure. And you do the same with copper. So if you have copper pipes or copper wires, you have to decide how much hardening. So they'll call it the hardening. What you do as part of the making of the aluminum or the copper, and you can do it with steel as well, actually. There is these very high strength wires. Even what you have in your mattress, a sleep mattress, is a small diameter steel wire that's been cold formed to raise the strength, thinking that you don't want it to yield anyway, because otherwise the mattress sags. So you get it very, very close to the, relatively close to the ultimate strength here and deformation behavior. Now, could it break? I guess sometimes, but it's loaded in torsion, so it's not a big deal. Another place where you use relatively cold hardened steel is some of the reinforcement that goes in concrete. And I think we can all agree why you do that is, let's say I have this big concrete cylinder for high pressure water pipes. We have those a lot across the country. Well, the concrete is never going to be able to deform anyway. So why would I put a wire in there that can stretch to 300% before it breaks? It doesn't make any sense. I'm wasting my time. So what I do is I stretch the wires as well. So for the amount of money I spend for the steel, it's 3 times stronger. So there will be, if we're talking about, that was the case of aluminum. If we're talking about relatively mild steel, and I don't want to go too crazy, but let's say this is a standard structural steel that you'll use in construction. So let's say I would start at around, so this structural steel, let's say I would start around 30 KSI. You can't really get it much lower than that. And when I mentioned about a factor of 3 here for the aluminum, for steel, well, it's almost a factor of 5. So you can get these to be 150 KSI with almost the same composition by cold hardening it and having this very big texture that raises your yield strength. Do you want to do that? Again, only in cases where you don't need that ductility, because you take those wires and you try to bend it, it will snap on you. That's how brittle it is. But the application, just so we're trying to be clear, so we have a water pipe. Let's say it would be taller than you. So I've seen them to 12 feet in diameter, so something like that. That would be up to, let's say the typical range would be 4 to 12 feet. And for the diameter, they come in segments. So you make the concrete cylinder in the shop, then you'll come and wind around the wire. So you go around and wrap, and it tightens the entire concrete to the point where all the concrete is really in compression, and the load is carried by these wires on the outside. So because we're looking at a very large diameter, and these wire would be very tiny, let's say it's, I'm talking about a 3 millimeter wire, it doesn't really get any kink when you're forming it. And that's the low-cost solution to be able to carry water at hundreds of PSI of pressure across Africa or here between the cities for supply. There's nothing really about this application that's a problem, although sometime it will break because you have these wires that are very, very tensioned, and if one of them is a little more than the other. I mean, this is not a very, very controlled process. You do your best. You roll the cylinder and you come and hope for the best. Sometimes you can have a little moisture penetration. You have what they call cathodic protection. So every once in a while, there'll be a couple of wires that start breaking. And what it means is they get the stress into other areas, and then it will grow over time, and then they have to go and repair. So there's nothing here that is perfect other than in the large scheme of things, when you have these sections that are, say, 40 feet long or so, it's the most effective way to make them cost effectively. And then you have to deal with maybe every 20 miles later, you'll have to go and repair a leak. But what they do, because everything here is a question of cost. If you try to make a 12-foot diameter cast iron or steel pipe, it's going to be extremely expensive, and it will also have some variation in it. There'll be some welding here and there, and it's not going to be perfect. So the idea here is they put a monitoring system, and this one is actually very nice because you can use acoustic emission. So they have sensors every 10 miles around the line with data acquisition, and when they hear an indication, they say, okay, there's a wire that snapped, okay, there's another wire that snapped, so then they try to infer where it happened so they can be proactive before there's actually a real failure. They locate the area and come and repair it. So these are typically buried pipes for water, but it's not buried very deep, so that's why it can go and do what needs to be done. Of course, if it's under a road, like in the cities, you hope for having as few of these as possible, because now when you're digging, you have other utilities, and it's a very complex process. So I guess this is a little bit of a side story, but it does tie into how do I make shapes, how do I make useful products for use. So that pipe, we almost went through all of it. So we have this inner concrete that doesn't have a whole lot of strength, but it's definitely water resistant. So there's no moisture getting to the wire. It's one of the characteristics it's built upon. And then you put the wires, and then you put another layer of grout or cement on the outside to protect the wires. So you benefit from the strength of the steel. It's called pre-stressed because the steel is in tension. And most of the concrete, especially on the inside, is in relatively high compression, so it won't start cracking. So we are kind of already probably expect what happens is, because when you cover the outside of these wires with another cement, that cement is not in compression. So it's typically going to be the one that breaks. So this will essentially be a degradation from the outside that happens in service with moisture getting into the grout or the concrete, as opposed to a degradation that starts from the inside here. So, yes?
I just have a question for that diagram. So
yes.
After you reach the ultimate tensile stress, you go down, right? So does it apply for the one when you do the hardening as well, so you go down faster?
Okay, well, very good question. So this curve here is for tension. When you roll, even if it's at ambient temperature, you can get to hundreds of percent without breaking it because all your stresses are compression. So that's a little bit what you do with the steel wire. Let's say you start with a wire that's this big. If you were to pull on it, it will deform maybe 30% and then neck and break. But when you do it with all these rolls, you can get it to much smaller, so you induce a strain of, say, 200%. And that's how you get it 2 or 3, 5, up to 5 times higher yield in compression. Then when you try to pull on it in service, it's still that 5 times stronger, but it's going to be able to deform, let's say, 4 or 5% now as opposed to 30% before it snaps. That's the big difference.
So this doesn't apply for the rolling, right? This diagram.
No, not at all. Yeah, on rolling, what happens is if you look at a true stress, true strain behavior, the steel never really gets softer. The only thing that happens here is it necks. So if you do it in compression, because you don't get the necking, it kind of looks like this, and it keeps going, and eventually it almost stabilizes, but it never goes down especially at ambient temperature. And before you reach this point, you're at somewhere in the order of 200-300% of deformation. Very good question. We went through that a little too quickly probably last time. So that's really what I meant here by when you cold form, you get higher yield strength. It's a lot more than just going around this curve in terms of the amount of deformation you can generate. But ultimately, you don't want to go too high if this is going to be an application in tension. If in the end you're going to be trying to pull on this, you need it to have enough hardening left. Because what happens when you reach here, is when you pull on it, it's going to start to neck and snap right from the beginning. So that's something you want to avoid. Yeah, if you go to the last lecture when we talk about necking, that's gonna help you a lot to explain what happened in tension that doesn't happen in compression. When I see here better dimensional tolerance, well, there is a big exception to that, which is, let's say I take a big plate that gets cold formed to become stronger, and you can do that with certain aluminum alloys like the 3500 series. But then if your process, then the next step is to go and machine that material, you'll have distortion at that point because the cold forming and all these roller action gets you a stress profile through the thickness. It's not homogeneous anymore, so you make it more susceptible to any kind of bending and distortion when you machine it, especially if you don't machine it symmetric one side to the other. So let's say we have just a standard plate that was cold formed. What happens, let's say it's always a little hotter in the center than on the surface. So when it cools, it's going to shrink a little more here. So you'll have tension in the mid wall, and then you get a little compression on the surfaces. So if I'm taking the compressive layer on one side, then all of a sudden it acts like a spring, and it's going to bend on me. It's a very significant effect. So a lot of times, if you want precision and less trouble when you machine, you have to use a grade that doesn't have a lot of this residual strain in it. It's not easy, because if you go for an aluminum alloy that has a high strain, a lot of times it has gone through a heat treatment, and that's why you are getting some distortion when you machine it. What else can you do? A lot of things, and we haven't talked a whole lot about drawing. So these are just other processes that you use with steel. And we'll try to go through them quickly. I'll give you a few examples. So the drawing, essentially you're pulling at the same time that you're reducing it. It doesn't have rolls at this time, so you have a lot of friction when you're drawing, and you need a material that has a lot of work hardening. Otherwise, it's going to break on you. So that's a requirement. So if you don't have a whole lot of hardening, let's say you're talking about aluminum that you're trying to get into a shape, whether it's a wire for electrical situation or any kind of profile shape to make prototypes. I mean, there's a lot of aluminum that's done by extrusion. So in that case, you're pushing the material into the die, and it comes on the other side. So you can't make all shapes because you need the extrusion to hold in there, and we'll talk about how you make pipes a little later. If we keep going, deep drawing, that's the example of the aluminum cans. If you take an aluminum can, it's got the underside, goes all the way up, and then there's only one joint for the top. So the way you get there is your shape has a hole. You come with a flat plate. You start coming down into it, and it stretches the walls. So that's why you have a thick bottom of your aluminum can, and you have a very thin wall around it. How can you do that without breaking the aluminum? Well, they use a grade that has a lot of work hardening. So when this section tries to get thinner, it becomes stronger at the same time. So this curve looks exactly like this. From the yield, it's going to go up a lot. The other thing that you can do when you do deep drawing is, let's say you start making that shape, it looks exactly like that, and then the next step would be you'll break somewhere. So what you do is you put it to the oven, eat it up, get it softer again, and then you come back and do another step. So it's not uncommon to do deep drawing in 3 steps, 2 or 3 steps, 4 steps, just because each time you get to soften the material and you gain, again, that hardening that allows you to not break. So you really are introducing a lot of tension when you're on the sides of these. Foraging is slightly different. So in foraging, you're mostly introducing compression. So you start with a little cube, and you can go through a series of steps of making a shape. And this one here is a foraging that has a number of very, very intricate details. It's going to have the stamp number and all of that. And if you didn't know at first, the first time I picked up this side, I wasn't sure it was a foraging. But when you flip it over, you'll see that lip here. It's not regular all around, that lip. Well, that's not from a casting or machining. This is essentially the proof that this was forged as opposed to anything else.
So it was initially forged and then drilled?
Yeah, I think you really just start with a ring. So you make a pipe, and you cut it in small rings, and then make it into that shape from there. And at the end, they had to cut the treads. That was the one thing that was machined. The reason they did it for this one is this is oil or gas piping, so you don't want any fitting to be brittle. If it was water, it's not interesting, but a water leak is not as bad as oil and gas. So That's one reason why this complex shape wasn't cast but forged. It's a lot more expensive. You can think of all the tooling to heat up and then come and hammer it down to that shape. There's a lot of forces involved. It's very dimension specific. There's a few other processes that are used. Stretch forming is you take a sheet, let's say aluminum, and I think I have an example, so I'm going to switch. Bending, you guys know, you just take a plate, you have a die, and you get it into the shape. These processes have been, now it's very easy. Even if you try to make a prototype, you can draw in SolidWorks what you like, and you get these shops to make all these bends for you very, very precisely. It's become so much more automated than even 10 years ago to make a almost like an entire box out of one plate that's cut and bent into these different corners. So bending is a very useful process, and shearing is just for separating parts. So in stretch forming, I guess I want to emphasize it because it brings a few concepts together, some concepts that we've discussed. So let's say I take a flat plate and I'm trying to get a very, very precise profile for that fuselage of the aircraft. Any change from the intended geometry is costing me a lot in terms of aerodynamic resistance. It's also making that the piece don't fit when you try to put it together. So what you do, instead of using stamping, which is very similar to this, you take a plate and you give it into a shape. By stretching it, what happens is you get the shape by having the material flow over your template. And the main difference, if we look at a cross-section, and that's done cold, right? So what happens in a cross-section, if I'm trying to stamp a shape like this, and I'm forming it, what happens is I'm going to get tension on one side and compression in the other. So if I'm looking at my stress profile right here, let's say this side is tension. So it's going to look somewhere like this because it's yielding on each side. So that's the loaded configuration, and when you unload it, it doesn't go to zero because you've deformed that shape. It's in maximum tension, maximum compression, and it's non-linear. So in the center, it stays elastic. That's what gives you your spring back on a. So if I try to stamp something, it's going to form and then it's going to come back a little bit. So it's a very complex process to get a precise shape, and I have residual stresses. So what the aerospace people do with the stretch forming is they get almost everything to be in tension. So there's going to be a very, very, very small difference here of tension because it's all being pulled, let's say 2% strain. So when you unload it, there's no stress. It's the main way that they have to get these double curvature shape. If you try to machine any of this, if you try to cast this thin, it's just not going to happen. So they make a lot of different shapes, and you see the equipment involved. It's pretty sophisticated, but a lot of the volume of surfaces on an aircraft are made this way. That makes sense? Why you do it? There's another advantage of doing it, which is when you create that 2% strain, you sort of prepare the microstructure for a heat treatment. So a lot of things kind of go in hand. So by deforming it, you get the aluminum to make the strengthening precipitates that you needed to create. So it's not going away. This has been optimized and works very well for reducing your residual stresses, getting your proper heat treatment, and getting a very, very precise shape because you don't have as much spring back when the stress profile is reversed when you unload. All right, we talked a little bit about foraging. So you have a lot of times you have multiple operation, and that was this example here. You can make very complex shape by forging or casting. This one is an injection molded part, and I brought it because when I looked at it, it failed. But I was very impressed by how they make an internal piping system just by having this housing and then these rams in different direction before you mold, and then you pull them out and you get all these shapes all around it. And when I open it up on the inside, there's just a lot of reinforcement and details, and that's all made at once. And it's a very relatively thin wall, so I was quite impressed by how complex it can get. Now, of course, you want to be making a lot of these. You can see this pipe. It's just all of the same. And essentially, it goes into an injection mold, and then you have the different ports coming into it. So you can do that at hot temperature with the forging is what I was referring to here. Okay, this is good. If you try to make tubing or pipes with a very controlled internal diameter and external diameter is where you'll use drawing a lot. And you can see in this case they have what we call a plug on the inside of the tubing. So you make it approximately to the dimension you want first. And in this last stage, where it's almost to shape, you get your very precise control of the OD and the ID. And a lot of time, that's also increasing a little bit your yield strength, if that's something you're interested in. So to be able to do drawing, you need the material to have this hardening, this stuff. So you don't want to do it at super high temperature. You do it cold enough that it creates the hardening when it's deforming, and so that helps you with your dimensional control. So a lot of times if you want a pipe that has very tight dimension, it's going to have to be drawn as the last step. So we'll move to plastics, and I think there's a good reason to bring them sort of together is we use a lot of them. We use a lot more plastic today than 10, 15, 20 years ago. It's just been a very, very gradual transition. Now, they're not perfect, but before I start talking about what they don't have, let's talk about what they do. No corrosion, right? In the sense of rusting. It's very flexible. You can make it in these complex shapes. I've circulated one. It will creep. So this process that we discussed for steel when it's red and I pull on it and it gets longer, that happens at ambient temperature with most plastics. And it's one reason why there's a lot of application like this is not a bad one. So we're assuming here that you won't sit on the chair forever, because otherwise it will sag on you, that you're going to be staying for 1 hour and then you go walk to another classroom. So there's a lot of assumptions when you design the plastic that's going to determine whether it's going to fail or not. So when we're talking about a pipe, that's a little bit the extreme situation where these pipes are actually used for 20, 50 years with pressure in them all the time. And we trust that plastic to do that. So the way you're able to do that is you run all these creep deformation tests. So creep is deformation under load over time. So here we have the time, it goes all the way to 50 years. And you can see that if I pull on stresses of the order of 12 megapascal here for polyethylene, I get to break it in a matter of 100 hours. So that would be, yeah, that would be leaving something very heavy on the chair coming back next week, and it sagged. Doesn't mean that it breaks, but it completely sagged. The other scenario where here you get the load cut off by a factor of 2 or 3, and then all of a sudden you get to 50 years and it's still holding strong. So it's just about the load that you're trying to put on. So I know this is a little bit of an introduction and getting you, but you can start to see that everything we've talked about today is factor of 2 or 3. You know, make it. Here we talked about making it 3 to 5 times stronger by cold working it. Over there I'm saying if you're going to use it very long time, you have to cut your load by a factor of 3 to 5. So these are the reason why we can use plastics, let's say for chairs on an aircraft, but we're never going to use it for something very structural unless there is reinforcement in it or unless the loads are very, very low. Which is hard to do on an aircraft fuselage or a primary structure. So the only place on a primary structure for the big aircrafts that there's a lot of plastic or composite being used is now Airbus has been the first one to bring a lot of these layered composite structures. So you will have glass or carbon fiber reinforced composite that works well in tension. And the reason for you able to rely on it is the fibers themselves don't really have that creep behavior and they carry most of the load. So, so that's why you're able to do that. So I have a lot of bullets here, but it reminds me to say that even though the plastics won't corrode, they can degrade a lot. So this polyethylene piping needs to be filled with an antioxidant package. So it's a little bit like a food preservative, for you can put in anything you'd like, so it doesn't start oxidation reaction that will lead to rapid failure. So depending on what you're going to use the piping for, you have to put more or less of that antioxidant package. So it's a very, very complex process, actually, to get it right. And you can make these very complex shapes. I'll pass this one around. You see, you can't really break it. And the way it's done on this particular case is you have the fitting, and then you are expanding the pipe to slide it over the fitting, and the pipe just shrinks back to this shape. So it's a very, very quick. You can make this entire assembly in 3 to 5 minutes if you're good, and you got your stuff cut. So the ring is to provide extra clamping force. So you have your pipe, you put a ring on, you have a tool that inserts and expands everything. You can slide it right over the fitting, and it's going to shrink back in a matter of about 30 seconds, and you're good to go. One thing that I really like about this system is it's very hard not to install it correctly. When you're thinking about everything else, if you're trying to weld or if you're trying to bolt things together, are you putting the right sealant between the threads? Are you tightening enough? It's a lot harder than this one. All you have to do is expand it enough so you can get in and push it all the way, and then you wait and it's fully installed. So there's a characteristic on this one that allows this to be working is there are barbs, and we don't see them, but let's say you have the fitting. There's on the profile, there's a little raised portion like a teat that the plastic engages over. So that's on the fitting itself. So when you sit on top of this, it creates traction so it's not going to pull out in service. And when I talk about service, the biggest load that would get this grabbing to pull out is not the pressure. I mean, this is a small diameter pipe, so the tension, let's say it's 100 psi, you got only 1/8 of an inch, so we talk about 20 pounds of tension. But when I start bending it like this, let's say it's going through some thermal cycles in the building, or there's something going on, these are the highest stressors. So if it was going to try to move and leak, it would be during movement like this, as opposed to just the tension from the pressure. Okay, so I won't get all the way to plastic forming, but let's try to get one more thing done. We've talked about dislocations and things like that for metals. So what we'll do now is talk a little bit about the spaghetti effect that you have on a polymer. So what happens when I'm just doing this here, it's not so much of a stretching of the bonds like we have with metals that's going on. First of all, it takes very limited force, even though this is a relatively thick wall. So what happens is the molecules themselves move with respect to each other. And I want to explain very briefly to you the different ways it does that. The first effect is, yeah, there'll be some stretch. There'll be just a very, very small local rotation of the carbon-carbon bonds that gives you a certain elasticity. But then what you do is you really have one chain and another, and they'll move a little bit with respect to each other. It's just going to be, one of them is going to turn a little bit and allow for a side group to move forward a little bit. And that's a little bit of relaxation inside the same shape. So nothing really has changed very much. It's just sliding a little bit by allowing a little movement. That's the viscoelasticity part. And then the viscoplasticity is then all of a sudden the two chains start moving significantly. The center of mass is changing with respect to each other, is one way to think of it, significantly. It takes more time, but when that happens, then you don't really have a full history of where you were to begin with. You really are having flow that is not necessarily going to come back, because you're losing that history. When you had these little side movement that I talked about, overall, the molecules are still arranged the same way. So when you take the load off, a lot of times that goes away. So that's why if I'm doing this like this, and I let it go, there's the elastic, and then it keeps going up and up and up and up and up. That's the visco part. Why do we care? It's affecting everything when you think about polymers. We've talked about the polymers when we talked about casting, that they have these ferrolites, or they are essentially semi-crystalline. And what happens is everything we talk about, all that visco aspect, happens in the amorphous zone as opposed to in the small crystals. So there's going to be a limit on how much you're going to have this before the crystals becoming unhappy. If you didn't have this, like polycarbonate, for example, does not have a spherulite structure. It's perfectly amorphous. It's just randomly organized throughout, and that's why I get a lot more deformation before anything happens to it. So you probably all know about nylon cords. They are relatively strong, and they don't deform that much. They don't act exactly like steel ropes, but they're pretty strong. And the way you do these is just by ambient temperature deformation to about 500%. You go from this ferrolite structure to a microfibril structure where you've organized all these crystal nodes are all aligned, and it's a fairly permanent process. And you get your strength by forcing all these amorphous zones to now becoming kind of on the side as opposed to part of the system. So when we were here and you try deforming this, it's a little bit like a composite in parallel. So you have the stiffness of the crystal and the stiffness of the amorphous zone, giving you your compliance. But when you start being really, really organized here, you essentially align your reinforcement, so it's almost like making a composite. The nylon is a little bit of a form of the cord. In the cord shape, it's becoming like a composite where you have these relatively strong fibers that are all these crystals that line up, and then you have the polymer between them. So that's done relatively cold temperature, and that's why when you take the nylon to begin with, it's fairly soft. And it has to go through this amount of deformation before it becomes very hard. So that's what I had for you guys today. Thank you.